Welcome back to this next video in which we are discussing the alternating groups. Okay, right. So in this video what we're going to do is define the sign of a permutation from the symmetric group on the set of n elements. Okay, so we're going to define a mapping which will be called the sign mapping and which will be denoted by epsilon, like so. So epsilon is going to be a mapping that will take any element of the symmetric group on the set of n elements and spit out either +1 or -1. So it's going to attach to any element of the symmetric group on the set of n elements +1 or -1, and what remains to be seen is what is the condition for it to be +1 or -1. Okay, now +1 is going to be for even set permutations and -1 is going to be for odd set permutations, and this is going to capture what we've discussed in the previous video, i.e. whether when you decompose the set permutation into a succession of transpositions you end up with an even number of them or an odd number of them. However, the way we are going to define this looks quite different. We're going to forget this for the time being. We'll come back to this and see how this other way of defining it captures this, but initially it's going to be very different. Okay, so the way we're going to define the sign of a set permutation will be consistent with this, but it'll take us a little bit of effort to understand why. So what we're going to do now is see the way that we define the sign of a set permutation. Okay, and I'll just add that if you have sign +1 you are called an even set permutation, and if you have sign -1 you are called an odd set permutation. So writing this out over here as well, the sign mapping will take every element of the symmetric group on the set of n elements and it will attach to it either +1 or -1. So we want to now see how we're going to define this mapping. Okay, so the way we're going to define this mapping is through a certain polynomial. Okay, a polynomial which I'm going to call delta, capital delta, like so. Now do not worry if you do not know anything about the rigorous theory of polynomials. You do not need to. Okay, classical knowledge from classical algebra will suffice, and in fact you don't really need any of classical algebra, only the very basics. Okay, basic understanding of how to manipulate polynomials. Okay, really the polynomial that I'm going to use here, this delta polynomial, it's just a visual way of capturing the concept that I want to capture about each set permutation, and you'll understand what I mean by that once I've actually shown you what we're going to use this polynomial for. Okay, but firstly let me just tell you what this polynomial is going to be. So I'm going to need a different polynomial for each different symmetric group on the set of n elements, so for each different n. Okay, so it will depend on which n you're using here. So if you're working with the symmetric group on the set of 3 elements, you'll need delta 3. If you're working in the symmetric group on the set of 20 elements, you'll need delta 20, etc. Okay, so the way I'm going to define this polynomial is it's going to be the product, so I'll put a big pi symbol like so, over I and j, okay, of xi minus xj. And now I and j have some constraints on them. I has to be strictly less than j, and I is allowed to be greater than or equal to 1, and j has to be less than or equal to n here. Okay, so that is how I can write out delta n then. Now of course whenever you see something like this it does look awfully confusing. This bit down here looks awfully confusing. Okay, if you're not totally familiar with the pi symbol that might look totally confusing. So to get some intuition for this, let's do some concrete examples. Okay, or a concrete example. I'm only going to do it once. Okay, so we'll do the example for S4. So we will work out delta 4, which is the polynomial we'll use for S4. Okay, so this is going to be then the product over I and j, where I is greater than or equal to 1 and j is less than or equal to, and now you insert in 4 there. Okay, so what we'd have to do is construct these little terms here and product them all together. Okay, so what would we actually do here? Well, let's start with I equaling 1. So we start off by setting I equal to 1, and then the question is, well, what can j vary over when I is equal to 1. So when I is equal to 1, j has to be strictly greater than I. They both have to be natural numbers. Okay, so j could be 2, 3, and up to 4. Okay, so we'd get x1 minus x2 then we get times x1 minus x3, and then times x1 minus x4. So that was just when I is equal to 1. I've let j vary over 2, 3, 4. I couldn't let j equal 1 because remember j has to be strictly greater than I. Okay, now let's move I upwards. Let's go for I is equal to 2. So we'll have x2 now. What can j equal? Well, it can only equal 3 and 4 now. So we'll get x2 minus x3 and then x2 minus x4 here. Finally, when I is equal to 3, we'll have x3 minus x4. I hope you're getting the idea of this now. And we couldn't let I equal 4 because then what would j equal? There wouldn't be anything for j to equal. Okay, so this now is our polynomial here. Okay, so this is delta 4 constructed for S4. Of course, this thing will end up being much bigger if we're working with S20 or whatever. Okay, but here's a nice example of constructing it for S4. So I hope that's giving you some intuition as to what this means. So you can construct this polynomial. And as I say, really we're just constructing this to visually capture a concept about each of the set permutations in the symmetric group on the set of n elements that we want to capture. And it's difficult to say what that concept is, but you will see that concept when I actually show you what we're going to do. Okay, so what we're now going to define is a way for each set permutation to act on this polynomial. Okay, so if sigma is an element of Sn, I'm going to now define a way for sigma to act on the polynomial delta n and map it onto something else. Okay, and as I say, this is the concept that I want this polynomial to capture here. So how is this going to work? How am I going to define this? Well, I'm going to define it to map it onto another polynomial, which I will define similarly. It's still going to be the product over I and j, okay, where again j is less than or equal to n, and I is greater than or equal to 1, and I is strictly less than j. But now what we're going to do is we're going to have sigma acting on each of the indexes here. So we'll have sigma of I minus x sigma of j here. Now of course sigma acts on the indexes very naturally because remember sigma is a set permutation on the set of elements 1, 2, 3, 4 all the way up to n. Okay, so sigma is going to send all of the elements 1, 2, 3, 4, 5, 6, 7 all the way up to n onto some other elements in that set. Okay, and indeed I and j are in between 1 and n here, so that's a very natural thing to define here. Okay, and we'll get some other polynomial as our answer. So again, to get some intuition for this, let's actually just do an example. So I'll go over onto the other side of the piece of paper and do an example. So again, we'll work with S4 and the polynomial delta 4 that we've already constructed. Okay, so we will need some sigma to be working with, and we'll just stick with this 4 cycle. 1 goes to 2, 2 goes to 3, 3 goes to 4, and then 4 goes to 1. So this is what sigma's going to equal. And now what we want to work out is what is sigma of delta. Okay, so I want to work out what is sigma of delta. Well, actually, to do this, it would be helpful to have delta sitting in front of us. So let's just recopy out what delta is equal to. Delta, remember, was this polynomial where we first let I equal 1, so we had x1 minus x2, x1 minus x3 times x1 minus x4. We then let I go up to 2, so we had x2 minus x3 and x2 minus x4, and then we let I go up to 3 and we had x3 minus x4, like so. So there was our delta polynomial. And now what we want to do is let sigma, this 4 cycle here, work on delta and turn it into a new polynomial. So let's do that. So the way, remember, that we do it is we go through each of these terms and we let sigma act on the indexes. So this is going to be sigma of delta here. So when sigma acts on 1, it will send it on to 2, so that one becomes x2. When sigma acts on 2, it will send it on to 3, so that one will become x3 here. So that's that first term. Now let's do the second term. So again, when sigma acts on 1, we'll get x2 here. When sigma acts on 3, 3 will go into 4, so this will become x4 here. And then next term, so again, sigma acting on 1 will give us x2. Sigma acting on 4 will give us x1, so this becomes x2 minus x1 here. Okay, so that's where that one goes. And then the next one, so sigma acting on 2 will send it on to 3. Sigma acting on 3 will send it on to 4, so this becomes x3 minus x4. So that's that one. Next one, x2 minus x4. Sigma acting on 2 sends it on to 3, so we'll get x3. Sigma acting on 4 will send it on to 1, so we'll get minus x1. So that will be that one. And then finally, this one here, sigma acting on 3 will send it on to 4, and sigma acting on 4 will send it on to 1, so we'll get x4 minus x1 here. So here is the answer as to what sigma acting on delta is going to equal. Now, I claim that what we've ended up with here isn't actually that dissimilar from the polynomial we started with. In fact, actually, it's going to be identical to the polynomial we started with a few little alterations. Okay, so let me show you this. If we look for this term here, x1 minus x2, can I find something that's very similar to it? Oh look, I can find x2 minus x1 here, just the negative of it. So what I could actually imagine doing is pulling negative 1 out of this, and then turning that back into x1 minus x2. Okay, this one here, x1 minus x3, here is x3 minus x1, so again, pull the negative 1 out, turn that back into there, that one's still present there. Okay, look at this one here, x1 minus x4, there's x4 minus x1 over here. Again, pull out a negative 1 and you can return that to x1 minus x4. Next up, x2 minus x3, that's there unaltered at all. Okay, x2 minus x4, that's here, still unaltered. And x3 minus x4, that's there as well. Okay, so now actually, this is the same polynomial, just with a few negative signs stuck out the front. So we'd have negative 1 to the power of 3 for, which ones did we alter? These 3 had all changed. So this one here, and this one here. And then it's just negative 1 to the power of 3 times delta. So sigma has not altered delta that much, basically. It's just caused there to be this power of negative 1 out the front. And in fact, this is something that extends more generally. In fact, if we have sigma, oh, and by the way, this was delta 4 in particular here that we were working on, so I'll just stick the 4 down there. Okay, more generally, if we've got sigma, which is an element of the symmetric group on the set of n elements, my claim is that if you let sigma act on delta n, what you will end up with is just negative 1 to the power of some k, let's say, times the original polynomial delta n, i.e. all that sigma actually does is flip a few of them round a little bit, but overall the polynomial remains the same. Now why is that the case? Why is it the case that you will always get every single one of these terms appearing back again, if albeit flipped around? Okay? Well, that has to do with the fact that sigma is a bijective map from the set 1, 2, 3 all the way down to n to itself. Okay, so let me just draw this out here. So if I've got a picture of sigma here, here's the set 1, 2, 3 all the way down to n. Okay, and I'll copy it out again. So here's the set again, 1, 2, 3 all the way down to n. Okay, and sigma is a bijective map from this set to itself. Okay, now if you consider creating a very similar map from sigma, which is going to act on the set of pairs, unordered pairs of elements here, okay, which is effectively what we're doing here. When we construct this polynomial, we have taken every possible pair of elements from the set 1 to n. Okay, so look, I've got 1 and 2, 1 and 3, 1 and 4, those are all the pairs involving 1. Then I've got 2 and 3, 2 and 4, those are all the pairs involving 2. Okay, well, all the pairs involving 2 that don't involve 1. And then I've got this pair 3 and 4. That is in fact all of the different pairs that I could possibly come up with where I don't count the different orders as different pairs. Okay, they're all of the unordered pairs of this set of elements 1, 2, 3, 4. So in fact these polynomials, the terms of the polynomials, are representing all of the pairs that you can possibly come up with of elements from the set 1, 2, 3 all the way down to n. And I claim that if we create a very natural map from sigma, which is going to be a map from these pairs, so if I now consider this set of pairs, so we'll have the pair 1 and 2, which I'll just put in a bubble here, we'll have the pair 1 and 3, etc., all of the pairs here. I claim that from sigma I can create a very natural map, I don't know what to call it, I'll call it sigma prime here, from the set of pairs to the set of pairs, which is going to still be a bijective map. And the reason it will be bijective is because sigma is bijective. And in fact the way I'll define sigma prime is it will just go to a pair here and it will map each of the elements of the pair onto what sigma would map them onto. Oh, and by the way, I do need to stress these pairs here, they have to be pairs that are not the same. Okay, so I'm not interested in 1, 1, those pairs. It's pairs of elements of the set 1 to n, where you are not interested in the pairs that contain the same element twice, and you're not interested in pairs that are just the same pair the opposite way around. So I'm not interested in 2, 1 as being a different pair from 1, 2. Okay, I'm only interested in each pair once. Okay, so I'm not interested in pairs that contain an element more than once, and I'm not interested in counting different orders as separate. Okay, so my claim is that I can define this very natural bijective map from the set of pairs onto the set of pairs, where it just maps a pair onto the new pair, which would be sigma of each of the elements. So 1, 2 would go onto the pair that contains sigma of 1 and sigma of 2, and I claim that this is going to be a bijective map. And to show that it's a bijective map, all I need to show is that it's injective, because we're working with a finite set here, and therefore if this map is injective, it's going to be bijective. It has to be. Okay, so how can I show that it's injective? Why is it the case that two different pairs cannot be mapped onto the same element over here? Well, if they were mapped onto the same element over here, it would mean that the two elements in the pairs have been mapped onto the same thing by sigma. Okay, and that would contradict sigma being injective unless it was the case that the elements of the pair were identical, i.e. you were talking about the same pair, okay, which obviously wouldn't be a separate element and therefore would be a contradiction. So indeed this mapping is going to be injective and therefore bijective. So when we do indeed apply sigma in this way to each of these pairs, which is what we're effectively doing, that's all this polynomial is meant to really capture. It's capturing all the different pairs of elements of the set 1 to n that are not pairs where the element is the same in the pair, the elements are the same, and where we're not counting the different orders. Okay, and we're applying effectively the equivalent of this mapping. We're saying act sigma on this one and act sigma on this one, like so. Okay, and it will end up being injective here, so you will, well, bijective even. You will end up with every single term of the polynomial coming back, even though you might have flipped them around. Okay, and here is slightly different from here because we do care about order here. We then are saying, okay, let's flip the term back round and pull out the negative one. Okay, so I hope you now understand that mapping, and I hope you understand why any element of the symmetric group on the set of n elements will act on this polynomial delta n to give negative 1 to some power times delta n. Okay, right, so now I'm ready to define how we're going to define the sign of a permutation. So the sign, remember, is going to be a mapping from the symmetric group on the set of n elements to the set containing +1 and -1. And the way it's going to work is this sign function is going to take any permutation in the symmetric group on the set of n elements, and it will map it onto +1 if the power out the front here is even. So if k is even, okay, so what you do is you say, okay, I will work out what sigma of the polynomial delta n is going to be equal to. I will get something of this form, negative 1 to the power of k times delta n, and I've just realised it's written out there, but never mind, I've copied it out again. Okay, and if this k value here is an even number, then I'll give that permutation the number plus 1. And if it's an odd number, I will give that permutation the number negative 1. And that's how we're going to define this sign mapping, and it will indeed ascribe to every permutation plus 1 or negative 1. So indeed, this 4 cycle, which we did the example of here in the symmetric group on the set of 4 elements, this would be an odd permutation because 3 is an odd number, so it would be ascribed the number negative 1 by the sign function. And you'll note how, oh look, if we go back here, it had an odd number of transpositions in this this decomposition into a succession of transpositions, so it is looking hopeful that maybe this sign function will capture exactly what we wanted to capture over here. Okay, I think we'll have a break here now that we've defined the sign function, and in the next video what we'll start to see is that this sign function can actually be viewed as being more than just a mapping from one set to another set. You can actually view this as a group homomorphism if we view this as the cyclic group on the set of 2 elements, and studying that is going to lead us to the conclusion that this actually captures exactly what we wanted it to capture in terms of the parity of the number of transpositions you need in any transposition decomposition for a certain element.